There we go. So we should be recording, and I will hand the floor over to Group 14 to share with us their design.
All right, y'all ready? I'm going to go ahead and share my screen. Hopefully this works. Okay, I think we're good.
Yep, there
Can
you
y'all
go.
see that?
Yes.
Awesome, perfect. Okay, well, welcome. Good morning. We are Group 14 from EML4501, Mechanical Engineering Design 2. This morning, we're going to be introducing our product MATE, which stands for Microbiological Autonomous Testing and Experimentation Device. To be completely honest, we chose that name entirely because of the MATE function within SOLIDWORKS. We just had a laugh over that one day because somebody said SOLIDWORKS had to be Australian because they use the word mate for everything. So today we're going to give you a quick introduction to our Hedgehog concept, but before I move on, I'm going to let the rest of my group members introduce themselves. So I'll go back 1 second. All right, there we go. Yeah, so I'm Josiah Poole, like I said, and I'll hand it over to the rest of my group to introduce themselves.
Sam?
If you're talking, you're muted.
I think my mic is muted.
Yeah, you're
I can
you're
hear
good
you
now.
We can hear you.
Can you hear me now? Okay. My name is Sam Bunner.
My name is John Capeller. My name is Nartan Messer.
I'm Kyle Jagelski.
I'm Christian Michael.
Matt Mitchell.
All right, and like I said, I'm Josiah Poole. So like I said, we're gonna do a quick overview of the Hedgehog concept, tell you what that is, how that maybe changed a little bit throughout the course of the semester, give you a quick product overview, touch on a few of the subsystems, and tell you about how we came to the decisions that we did in terms of the final design. We'll show you the cost overview and the overall cost estimate that we reached after the final design was realized, and then give you a summary of the overall design and highlight some of the key features and unique design features. Hopefully we won't get lost in the weeds, so you'll have some time to ask questions at the end. So yeah, our Hedgehog concept is to be able to process the largest volume of cells, liquid cell culture media, in the quickest fashion possible by offering seamless transfer between compartments. And we also have adjacent culture monitoring platforms. And we'll talk about that a little bit later, explain what exactly that means. As we've moved on, we've kind of realized we focused our design a lot on passive liquid handling and waste disposal, and realized we had some interesting design features in terms of that. So our design kind of focused on that as well, but we still, I think, captured the essence of this. So we'll move on to the product overview, and I'll hand it over to Christian.
Thank you, Josiah. Yeah, as Josiah mentioned, our goals were to process liquids and to create a monitored culture that we could control to the best of our ability. And the main function of our design is to process cells for microbiological testing, as well as perform experiments and collect data, and the data being optical density and fluorescence intensity, which is the OD and FI in the first bullet point. And so that is kind of accomplished by our 3D motion system, which is kind of a series of tracks that will allow it to move in the X and Y direction, as well as an arm that can descend and move in the Z direction up and down, that can extract and dispense liquid from a reservoir into the well plates or test tubes, whatever we're using for experiments. That arm has a pipette on it that is controlled by a stepper motor. And we've run calculations on that, which we will get into once we discuss later. But we feel confident that it can offer an accurate and precise dispension of liquid or cells or whatever we're using. Additionally, to perform experiments, we use a cell shaking platform, which consists of essentially 2 orbital motors that are coordinated to allow the cell plates themselves to move in any direction we want, any patterns. Additionally, those plates, they'll each will be temperature monitored with a temperature control system, which kind of consists of a Peltier system and a heat sink. And again, we'll be touching to that later. It's just kind of a bird's eye overview. There's also an automated gas manifold that will kind of help us monitor the gas that's going into and going out of it, as well as sensors that are within the incubation zone that can help us monitor exactly the gas percentages, and then we can insert gases or take out as needed. The frame is made from 80-20 for the most part, which will allow us to have easier assembly times, easier assembly process and shorter assembly times, I should say, as well as access hinges for easy assembly and user interaction. Access hinges for user interaction. Just that we'll be able to, the user, the scientist running the experiments will be able to handle the well plates or test tubes that they're using, just take them in and out of the machine quickly. And finally, the overall dimensions, just so you have a scale of the device, is 32 inches by 42 inches by 36, which is about the size of at least the length and width is about the size of a standard lab bench, and the height is 32 inches. And next, we're going to go individually by subsystem to just kind of get a more in-depth look.
All right, thanks, Christian. So the first major subsystem we tried to address was liquid handling. You can see the customer needs there. So we realized that each component within the subsystem would be able to meet the 10-year lifetime requirement. We figured this one would be probably the most vulnerable to that because it's experiencing the most moving components. But all the motors, lead screws, mounts, and the motorized pipette itself are not, in danger of failing within that 10-year lifetime. We realized polyethylene met the chemical compatibility requirements because it has a rating of A for the majority of chemicals, and it also had the strength requirements to be able to withhold that lifetime. Our design is capable of fluid addition and subtraction with the motorized pipette because it has a plunger that moves up and down. So basically the same concept as a syringe that allows us to take advantage of the pressure differential to suck fluids back up when we need to. We're able to achieve the dispense rate between 225 and 300 microliters per second with the stepper motor that Christian may have mentioned earlier, and the rack and pinion system attached to the pipette. Our dispensing accuracy is plus or minus 0.3%, which falls within the requirements. And we take advantage of passive liquid waste disposal with our Pythagorean cup and our irrigation system, which I'll talk a little bit about right now, actually. So this was an idea that Trom clued us into and told us to kind of check this out. And we came up with this simple design, basically just an off-the-shelf funnel that you can buy at any hardware store pretty much. And we use PVC piping. And the way this works is you can see the bend that comes up through the funnel. And you would start with an initial level of fluid in there that is above the lower part of that bend so that gas isn't escaping. And as we dispense liquid waste from the culture monitoring experiments as they've concluded, and we're removing liquid from the well plates, we dispense them into the funnel. And once the liquid rises above that bend in the funnel, then it ends up emptying through the tube and out of the system. So it removes the need for a valve and takes advantage of just gravity-driven flow. So we've just got a tubing that runs through the funnel and an O-ring to make sure that's sealed off in there. And I think it's pretty interesting concept to just remove the need for any more automated waste disposal. And this is the waste neutralization and liquid handling are incorporated into the singular pipette system because we use the same pipette liquid handling to transfer cell culture media and to also neutralize the waste. So it's all in one, so it removes some complexity there as well. And we have versatile movement mostly in the Z direction, which allows us to reach the height of conical tubes and different varying depths in well plates, and also access the feedstock reservoir. The highest technology readiness level in the system would be a 9, just because the lead screws and most of the motors have all been used in real world settings and proven to operate in those situations, almost identical to what we're using now. And the lowest one, which we would default to, would be technology readiness level 3. And just one example of that is the pipette rack and pinion system, since we made a custom design for that. And so it hasn't been tested in an experimental lab setting yet, but we have conceptually analyzed it to prove that it could meet requirements theoretically. So we'll move on to the next subsystem now.
Thank you, Joe. So our next subsystem is the culture condition control, which mainly has to consist of shaking and heating the well plates, which we briefly touched on before, and then keeping a specific gas composition within the system and being able to change it as needed as new cycles start. So the customer needs that were addressed for this subsystem are the hibernation time of being able to hibernate in culture from 1 hour to 2 weeks, a closed loop control so that the system would, once made, be coded so that any cells that, based on the OD and FI measurements, the cells have been decided that they need to go through another cycle, or that they need to be taken out of the system or just completely disposed of because cells died, or whatever the case may be. There's a closed loop control that once those measurements are read, the decision will be made from there. Excuse me. We have the culture temperature range for each individual well plate that is between 4 and 70 degrees Celsius, that will be controlled by this, you can see it in the lower right image of the slide, this thermoelectric cooler that allows for heating of the well plate and being able to change the temperature, again, based off of a user interface system, to be able to decide about what temperature you want things to be heated at. This will allow for a variation. And in the same vein, we have uniform heating within that thermoelectric cooler, because it's one plate and one plane that is heating all of the wells. So there's no temperature gradient between each one. They're all going to be heated at the same level. We also addressed effluent gas capture, which in our case, you can see it on the top right image here. On the lower right outside of that image, there's a Venturi pump connected to the system. So you take pressurized air and you'll attach it in the direction of airflow. And then once you decide that you want gas taken out of the system, you turn on the pressurized air and you create a vacuum. And we have sensors within the system that are monitoring the composition of each gas. And we will be able to take out gas as a cycle ends so that a new cycle can start with a new gas composition. And in the same vein, gas control. So on the left side of that same image, you'll see a gas manifold that's connected to a volumetric flow meter. And there are 5 valves on the manifold as well. So we have the 5 different gases that you would connect to the valves. And as I said, there are sensors within the system to monitor the composition that each gas has. So you put in as much as you need through the volumetric flow meter, and there will be gas within the system. OD and FI measurement, which was touched on in the product overview and in liquid handling. We have the optical density sensor that will measure, again, the optical density of each individual well and fluorescence intensity as well. We have that sensor. And then monochromator versus a filter. So in the same vein as the optical density, we have an OD filter that will allow for precise measurement of optical density. And then the light intensity and wavelength. So the LED plate that we have each well plate sliding over to will be at the 640 nanometer wavelength, so that they are that is the maximum wavelength that they can have without the cells being affected by any other wavelength. And we also have a camera at the top of the system with LED lights next to it for a visual representation of everything that's going on inside the system. So a couple of key features, like I was just mentioning, we have a camera at the top of the system paired with those red LED lights, because the side panels, which will be touched on in a second here, are opaque. You can't see the process happening. And we thought it would just, we thought it would be interesting and beneficial to be able to see the process as it goes on, especially for the sake of if you need to manually stop the system if something goes wrong and for some reason has not engaged, you'll be able to do that on your own. And the red LED lights paired with the camera won't mess with the cells at all because of the 640 nanometer wavelength that they would have. You saw in the very first slide, the entire system, we have 6 weld plates sitting in the system at the same time, rather than just 1, 2, or 3. We have 6 that could be going simultaneously. And then I mentioned the gas manifold. One important thing to note about it, which is mentioned here, is that it's very close to the system, and that gets rid of the worry of residual gas being leaked or residual gas going inside the system that you didn't want in the first place. The proximity of the manifold to the system gets rid of the worries of that. And then for the technology readiness levels, it's in the same vein as liquid handling. The highest level would be many of the OTS parts. In this case, we just mentioned the volumetric flow meter. It's been tested in systems very, very close to this, and in scenarios very similar to this, tested, analyzed, and proven. So that's at a technology readiness level of 9. And then our lowest level would be those sterilization channels that he mentioned in liquid handling as well, because they also have to do with culture condition control. That is specific to our system and unique to our system. And we have conceptually and analytically gone over them and proven them on paper, but they have not been tested in any relevant environment. So that would receive a technology readiness level of 3. So with that, I will hand it over to the frame subsystem.
Thanks, Kyle. So for the frame subsystem, the customer needs addressed are shown. These include fitting inside a standard laboratory facility, accommodating a standard wall outlet, being easily accessible to the user through hinges touched on later, as well as ease of assembly through the 80-20 extrusions we mentioned earlier. We wanted to have a 1.15 factor of safety to ensure that the structure is safe to use. We also wanted to have a manual emergency shutoff, as well as an automatic shutoff, and wanted to have no external fixtures. So some of the design features of the frame, we used 14 gauge sheet metal side panels with hinges for easy user access. So the user can lift one of the panels to have just a full access of the inside of the assembly. As touched on earlier, we had a size footprint that accommodates a standard laboratory benchtop, as well as being able to fit through laboratory doors. And we used 80-20 for the frame to provide modularity and more ease of assembly in terms of assembly times. And we have the integrated push button mechanical safety shutoff. And to maintain gas composition, we have a rubber contact seals on the sheet metal plates integrated into the 80-20 to prevent gas leakage and maintain internal gas composition. As far as technology readiness levels, the highest level would most likely be the 80-20 extrusions, as they're a proven commercial product. And the lowest level would be the automatic shutoff, because that requires certain software implementations and circuitry that as of yet have not been thoroughly analyzed.
All
And
right.
with that, I'll bring it on to the plate movement subsystem.
Thank you. Okay, so for our plate movement subsystem, we decided that the customer needs that need that are applied to this subsystem in specific are 21, 22, 23, 31, and 32 as following. So we decided that for our plate movement subsystem, we have the well plates basically have to be fully enclosed. So for that, we have a well plate cover with a hydrophobic film over it, which it covers the well plates to make sure that they're enclosed while mixing. And then the next one is it must accommodate standard well plate sizes. So our well plate is designed to fit a standard well plate size, and if other sizes are used, we could have adapters to make sure that it fits the well plate, especially like the next part too, where it's conical tube sizes. We would have to have an adapter where it fits onto the well plate and it would lock in there. Next, we have linear orbital and double orbital shaking patterns. So for our plate movement shaker, we actually have 2 stepper motors, which can basically produce any 2D motion with a range of about 40 millimeters outwards in a circle. And lastly, the plates can move independently from each other. So we have 6 separate plate movement subsystems in our design, with each one having independent plate movement. All right. So on the right there, you can see our plate movement design. We basically have 6 of these, like it was mentioned previously, with 2 stepper motors. So if you look at the design on the bottom, we have the 2 stepper motors with a slight offset between each one. So it's basically like a 2D robot arm where it can produce any 2D motion. And not pictured in our on the right here, we also have a cross-contamination prevention cover, basically like a lid that comes over the well plates while they're on top of this plate movement subsystem. And that would have, like I said earlier, a hydrophobic film to basically prevent any liquid residue on it. And we also have we can clean that well plate cover as well with a pipette. So temperature-based features. So on the top, you can see we actually have a copper plate, and that's basically used to locally heat the well plate to like a uniform temperature pretty much. And we also have a thermistor embedded inside that, underneath that copper plate, basically to measure the temperature and have closed loop temperature control. We also have, so I guess I didn't mention what heating we're using. Underneath the copper plate, we have a Peltier cooler, which can basically pump heat from one side of it to the other. So if we want to cool the well plate, we would pass some electrical current through the Peltier cooler, and it would make the top cold and the bottom warm, or it would do the opposite. And underneath that, we have a heat sink. So if we were making the top cold, the bottom would be warm, we would be able to wick away some of that heat to make it like cooler on the top. In between the copper plate and the heat sink, we actually have insulation too, to make sure that we have efficient cooling or heating on that top well plate cover. So technology readiness levels, we have the thermistor, which is level 9, because that's been used in many different designs, and that's a proven method of temperature control basically. Lowest level would be the double orbital motors, so double stepper motors really. So we designed these 2 stepper motors on top of each other with like arms. So it's kind of like a 2D robot arm. So we have analytical calculations for it, but we don't have it proven exactly. So, okay, next one. All right, next system, we have the user interface. Thank you, Narutama, for doing plate movement. So the customer needs addressed by this subsystem, as you can see on the screen. I'll go through each one. So first off, customer needs 6, includes a fail-safe system and a software alert for condition control failure. So the user face itself is a 7-inch touchscreen made by Raspberry Pi. So this would address this feature by having a digital fail-safe system and software programmed alert when culture failure were to occur. That would be programmed in, so there would be a visual notification
telling the user that there has been an error in condition control. Next up, so more visual indicators. One specifically, and most importantly for system on and off, there would be a programmed control to turn on and turn off the system via the touchscreen. And a visual indicator for mode and time duration. So there'd be a setting where the user can determine the type of mode based off the experiment they wish to perform. And then for each experiment, there'll be a time monitor that will be displayed showing the user how long the experiment has been conducted, up to 2 weeks, of course. And then more importantly is error notification. If one were to occur for culture monitoring, or mechanically, if there's an error to occur as well, a notification would be sent to the user and they could clearly see that via the touchscreen. Next customer need 11, a very important one, is the total cost cannot exceed 10,000. Thankfully, we were able to achieve this for not only the subsystem, but for all subsystems or the whole system, with a total price or budget of $9.6 thousand. So that customer need is met and will be addressed later in a cost analysis. Next up, control parameters can be changed via programming. So this Raspberry Pi provided touchscreen was determined out of all the concepts to be the most programmable in achieving all the functions. It is directly wired to the system itself, so there's no like wireless communication that may be interfered with and hinder controllability. Next up, must be intuitive user interface. So through programming, it's important that this is intuitive, and one way this software or interface can be intuitive is through like binary decisions. So the UI can be set up such that any user of any IQ level, like even students at younger ages, can intuitively use this, having the experience with other technologies, simple step-by-step process to set up the experimentation parameters and run it, and then observe data and transfer data where needed. Also, from previously mentioned, the camera feed would be displayed on here to whatever extent, potentially full screen, potentially minimized, and recorded and uploaded for analyzation later. Next customer need, this overall design does meet the BSL-2 lab requirements as noted from the overall dimensions. And then last customer need for the subsystem, the exterior dimension, exterior surface temperature does not exceed 55 degrees Celsius and interferes with internal temperatures. So moving on, next slide, please. Highlight some more, or touch more on some of these key features. Like I said, this will be attached directly to one of the sheet metal side panels. So it's attached, it comes with the machine itself. And like I said, directly wired. Total of 7-inch HD display, so it's clearly visible to any users. Completely programmable through the Raspberry Pi setup, and very simple to design and implement, which will be later used. Doesn't affect the internal temperature or even external temperature. The overall UI is within budget and very feasible. More on the TRLs, as you can see, there's kind of a theme, the highest being 9, with the touchscreen, human touch recognition feature of the touchscreen has been tested and proven. So therefore, it is feasible in the real life. And then control system itself, the software, which has yet to be created and implemented, would be a technology readiness level of 2, and the overall subsystem would default to that. And that sums up the user interface. We'll now move on to the cost analysis. So as you can see, the cost analysis was subdivided into off-the-shelf parts and raw materials, manufacturing costs, and assembly time costs. I'll start with OTS parts, which was the bulk of the budget. OTS parts include motors, thermoelectric coolers, gas controllers, optical monitoring devices, and the drivers and controllers for all that took up a majority of the price. And then I'll move on to Matt to take care of the rest of the cost analysis, please.
Okay, so the rest of our cost came from purchasing raw materials, which is mostly used for like all the motor mounts and like sheet metal walls, like PVC piping. And then manufacturing cost was calculated using methods we learned in class, mostly just to cut all the aluminum motor mounts. And assembly, we used a Berthold and Dewhurst like chart to estimate how long it would take to put together, and then used data from the U.S. labor statistics to calculate how much that would cost. Yes, our overall price is $8,802.
So just one more brief overview just to wrap up. Oh yeah, I guess got the message. Awesome. So we'll go very quick. Why mate? One, we have precise culture control. We use electrochemical sensors, which are more accurate than other methods of determining the amount of gas of each gas. Also, we use a mass flow controller with a short hose, as short as possible, to the gas tanks, which are going to create less residual gases and overall be more accurate, as well as a venturi vacuum, which can help us control gases exiting the system as we want it and not unwanted exits. Additionally, the experiments can run quickly. This is due to the seamless liquid transfer. We believe our liquid handling system is precise and accurate enough that it can minimize any kind of mistakes or errors, and therefore greatly reduce time and experimentation, as well as the condensed layout, which allows us to minimize travel distance and therefore minimize time, essentially. And finally, the whole design is economically favorable. It is simple and effective. We believe that we didn't do anything overly complicated, which will allow it to, one, break less, which is more cost effective, and two, we're not spending any unnecessary money on any unnecessary parts. And that is evidenced by the fact that it is within budget. So those are our strong points. And if you want to hit the slide, thank you for taking the time to listen to our presentation, and we can now open the floor for questions.
Okay.
So just real quick, Dr. Traum and I had a side conversation in here, guys. I'm actually going to go through my list of questions and everything with you after everybody else moves on to the next presentation. So I'm going to leave this for our representatives from Cummins and Northrop Grumman to, and our customer being Dr. Menezes here. But just be aware that you're going to be on the clock with me for a couple minutes after the presentation.
Okay.
Sure.
This is Tom Singer from Northrop Grumman. The heating and cooling device that you showed, that is internal to the structure, right? I mean, you've got a fan and a heat sink that's just taking heat out of your well tray and dumping it into the system.
Correct. Yeah. So we do most of our heating and cooling like localized. So we'll heat the well trays on top of the copper plate, and then we'll cool it too on the same plate. And then if we'll have like the extra heat, if it's cooling, the extra heat on the bottom will just be released into the enclosure.
And then what?
Well,
I think the thought we were banking on, or not banking on is the right word. We were deciding that the excess heat would be kind of like, we would use the natural environment of the laboratory as kind of like a natural heat sink through our walls, our aluminum walls. That was kind of our thought process for that, I guess.
So you've accounted for the temperature inside your chamber rising and make sure that you have enough cooling capacity, even with that warmer sort of local temperature. I mean, it's got to raise to start conducting through the walls and being dumped into the lab, right? I mean, so you've accounted for that in your heat calculations?
Yes, and we do have some backup slides if you're interested in the equations used and the methodology. If you like, I can share my screen with that.
You want me to stop
Actually, I
sharing?
don't have permission.
I think you have to stop
While
sharing.
while you're bringing that up, can I just ask? It looked like you were anticipating less than 1 hour assembly time for this system, based on your cost estimate.
Yes.
Is that feasible?
We believe so, based off all the Boothroyd and Dewhurst assembly time, the handling and insertion. The manufacturing itself would obviously take quite a while, but we believe that the assembly time would be relatively low, almost an hour. We believe that that is feasible.
It seems aggressive.
Yeah, I have the same kind of thought about that. I've assembled just simple coffee tables from IKEA. It's taken me longer than an hour. And this seems a whole lot more complicated than that. So I may need to revisit that analysis. I think an hour is very aggressive.
Mm-hmm. One other thing before I kind of maybe let you get back to the thermal stuff. You mentioned that the customer requirement is for a 1.15 factor of safety.
Yes,
Is that a reasonable factor of safety for lab equipment? Because I build airplanes, and that's a super sporty factor of safety for airplanes. And as far as I can tell, grad students with lab equipment aren't handling them, aren't analyzing them, aren't maintaining them to the same level that airplanes are. Certainly the risk is less, but I would expect to see a factor of safety on the order of 3 to 4 at least for something like this.
I believe that many of the subsystems would be in the range of 3 to 4. That the 1.15 was a minimum that we tried to hit, which was mainly based on kind of the size of the system and of course its weight and how it's the tabletop bench would be able to, with its load capacity and it being able to actually hold up the system. That would be really the biggest risk we feel. So if we were to go through everything again, I believe we would hit a factor of safety probably pretty close to a 3 or 4, but that 1.5 was a minimum that we needed to shoot for from the start and then build from there.
Sure. I guess I would ask, did that drive any of your design?
The 1.15, like it really just drove the size and weight of the design, which is after some of the concepts is how we came to something like 80-20 for a large majority of the frame, just for the sake of its modularity and its density.
Do you do any analysis to back that up, or is that on an extra slide?
For the factor of safety, yeah. So a lot of it was based on the weight of the whole system using the 80-20, and then everything else within the system for the tabletop bench. So that is our lowest factor of safety, which is about it's at the 1.15 or a little bit higher. Based on its size, and it's very close to the size of the entire bench. So the excess distance on either side is a little bit low. So that is our lowest factor of safety.
What's the overall weight of this thing?
I believe once it's all put together, I believe it is pretty heavy. If someone remembers the actual number, Tom.
So it was almost 200 kilograms, I think.
Holy moly. Where does that weight come from?
Motors, the sheet metal, all the 80-20.
Thick as your sheet metal that you've got 200 kilograms in there.
That's 450 pounds. That's an awful lot. I mean,
what's the safe? One of the customer requirements was it must be like movable by a single person. What's the OSHA requirement for safe lifting by a single person?
Certainly less than 400.
It's 50 pounds. Anytime you get a package from FedEx, that's over 50 pounds, it says 2-man lift. Or use a forklift or something like that. Like, you guys are 8 times higher than a requirement.
I apologize. We don't have much of an answer for that. It was a bit of an oversight from the start, and then once we got there, it was a little bit hard to reduce everything from there. So we just
How did you decide to go with the sheet metal?
that was based off of its cost to also meet the cost limit, which was also we felt was very important as well. It was to meet the cost, and it was the lowest cost that we could have for everything we needed for the frame, the outside walls, and for everything to sit on top of. It was the easiest to manufacture in terms of cost, and like I said, just in OTS part cost in general.
We also wanted something that was going to be it was going to be opaque. It wasn't going to emit any light through it, because the light waves from the lab itself would potentially interfere, as we kind of touched on with like the 640 nanometer wavelength for the light that was inside. We didn't want any excess light that could damage the cells and thus ruin the experiments.
Yeah, we had initially gone with, I think, tempered glass panels. Maybe been possibly been a little bit thinner than the sheet metal as well, but because of the light factor that Christian pointed out with the sheet metal.
It also helped with removing the heat from the system because it's metal, so it's like a heat sink to the internal air also.
Yeah, which you kind of touched on earlier.
So I think there may be a slight misunderstanding here about the 640 nm light. Let me ask you a question. What was the motivation for the red light again that you were going to stick on next to the camera?
Yeah, we thought it would be not necessarily meeting a requirement, but more of like a customer delight, I guess you could say. We wanted, because it is, not see-through, we wanted to give the experimenter a way to see what's going on visually. So we added a camera on the roof, and the 640 was just, the red light was just something, a way for a visible light that you could see with that wasn't going to interfere with the experiments, like I said.
Okay, so there are two statements there. One is that you were trying to block out external light, which is fine, but then you said you're going to put in your own light. So here's why that's potentially a problem. So I don't know if you understand what fluorescence intensity is. So the way it works is you have an excitation spectrum and then an emission spectrum. So if you are putting in a red light, that's basically going to excite any fluorophores that are in the cells at that wavelength. And so what that means is that you have effectively eliminated the capability for cells to have fluorophores at that wavelength, because if you're trying to see cells at that wavelength, you don't want to excite them to do something else, right? It's going to stimulate the cells to do something. So you basically have eliminated any experimental capacity to have fluorophores with that excitation.
Okay.
So you may want to revisit the red light thing, or you can get around it perhaps by saying that it's only on at a very short period of time, which is insufficient to excite the cells. That could be your cop out. But
We could keep it on when desired to see it, but off.
Yeah, or something along those lines. It's not something that. So I was listening very carefully, and I didn't hear you say anything like that, which is why I'm bringing up this point. You cannot have this permanently on.
Okay, got it. Thank you.
Okay, so sorry to cut off questions, but we're 5 minutes over, and we do have another group that's waiting that was supposed to start at 9:45. So I do want to just wrap up there, but Dr. Nemi is going to stick around with you guys. I think he had a litany of questions, and so he'll go through those. Let me stop recording.